I'm going to be done grading the exams either tonight or tomorrow. So be prepared for that grade when I do finally upload it. Additionally, I got quite a massive number of emails within an hour of this class session asking for when the homework was due. Now, y'all know how it is about asking at the last minute for these certain kinds of things. The homework's due Thursday. It's due Thursday. It's not due Tuesday. If I said it was due Tuesday, it might have been a misunderstanding. It's due Thursday. So if anything, that's good in your favor because that means you have more time. And so you can ask me questions after class about any of the homework questions. I really don't mind. So so that homework is due Thursday, and by that point when you turn it in, of course the exams should be done graded. So also the midterm, I've decided the midterm will be 2 weeks from today. 2 weeks from today is the midterm. So the question now remains, so if you're taking it in class, so it's going to be an in-class exam unless you request to take it remotely. You have to accommodate it. If you have to take it remotely, if you take it remotely for whatever reason, just email me. You have to email me. I'll give you until Thursday. If you take the test remotely, you got to email me by Thursday and let me know that you're doing that so I can set up the proper accommodations. Because there's this thing called ProctorU that you would have to use, and I have to get that set up as quickly as possible. So if you have to take the test remotely, let me know. Other than that, we'll just take it in class 2 weeks from today. So that's pretty much it as far as the midterm goes. So please let me know that information. If you have to take it remotely, just email me and say, I want to take it remotely. That's it. That's all I need. So other than that, that's all I can really think of. So does anyone have any questions, at least about anything coming up? It's a midterm in 2 weeks. Yeah.
Is it going to be through the end of chapter 3, or are we going to chapter 4 midterm as well?
It's going to include radians as well. The midterm will include radians as well. So we're going to get through, we have 3 class sessions, and then we're going to have a review session.
So is it going to be comprehensive with chapter 1?
Yes.
It will be, okay.
Yeah. It'll mainly focus on this stuff, but there's going to be, math is naturally cumulative in nature, so it's hard to avoid it. So it will be the majority of the stuff we've learned after. So sines and cosine, law of all that stuff, and everything we're going to be talking about today and onwards. But there's just this natural recurring effect of mathematics that is just hard to avoid. So besides for that, and I'll talk more about that in the coming weeks. But let's go ahead and get started with the new stuff. So we talked about law of sines and law of cosines last time in class. So now we're going to move on to some application of law of sines and cosines. We'll be using it here. And this is talking about vectors. So for physics and engineering, vectors are used a lot. They're used to represent a multitude of things, including forces, direction, anything of that caliber. And so a vector, well, the way it's denoted, you might see at the bottom of the page here, it's just these rays. And so vectors have, so from a definition perspective, a vector okay. I guess I'm not the only one. Hopefully you all see this as well. Okay, that shows up. try this again. Let's try this again. Vector, thank you. Okay, vector has both magnitude, which is pretty much size in essence, and direction. So a vector is a directed line segment, so you can see the notation down here. And normally, so in text, a vector is sometimes notated as a bold-faced lowercase letter. In writing, you'll see momentarily, but in writing, it'll sometimes be written like this. It's hard to do boldface when you write stuff down, so we generally tend to call that V with a harpoon on top of it. They actually do call it a harpoon V. So the length of the vector is called the magnitude, and it has its own notation with absolute value bars. So if you see absolute value bars around a vector, it's asking for its size, its length in essence. Two vectors are equal if they have the same magnitude and direction. So the most intuitive example, just to sort of explain the notation and terminology, a car going 30 miles per hour in a southeast direction. Well, southeast is this way. And we would say that this is 30 miles per hour. Just nothing crazy. If we wanted to give this a name, we could call it V with a harpoon over it. And then it says, do the same for a car going 15 miles per hour in a northwest direction. Going northwest. 15 miles per hour, and we could call that, give it a different symbol. Normally, V's and W's are pretty natural. So just a way to explain the notation and some of the symbolism that's used here. So really, I should have drawn these to scale as a 30 mile per hour vector will be larger than a 15 mile per hour vector. So generally these are drawn to scale, so I should probably emphasize that. So notice 15 miles per hour would be half as much, half the length. That's sort of explaining a bit of the illustration behind everything. So vector addition. So the sum, or sometimes they'll use the terminology of resultant. And of course, that's just, they use a plus sign in between two vectors. There's really two ways you can obtain the resultant, or the sum of two vectors. So, and I'm going to explain this while doing example 2 down here. So one way is as the description says. So if you're looking for A plus B, you start off by drawing A. And then I'll use a different color to draw out B, but vector B is going to start where vector A ended. So vector B, it seems to be fairly long. So vector B would be right here. The resultant would be a new vector that starts at the very beginning, goes all the way up to where B ended at. So it starts at A and ends at where B ended. And so this would be A plus B. So that's one way you can do it. Another way you can do this is by having A and B pretty much jet off from the same point. So if you just have one point and you have both A and B extend from that same point, then you can form a quadrilateral or a parallelogram instead. You can form a parallelogram between the two. And the diagonal of that parallelogram would also be A plus B.
Is there going to be ever like a situation where you have to do parallelogram or anything?
Both of these have their specific practical uses, as we'll see in some applications coming up. One of them, the parallelogram, helps more. The other one, the initial way, helps more. We'll see in the applications, but both of these are helpful. If you're keeping up with my colleagues' videos or my videos, I only explain it the first way. And I did that until everyone who turned in the homework did it the second way, which was a way I never explained. So I found that kind of interesting. They all figured out that second way. So I figured I'd just teach both and you can do what you want. So if you watch the videos, I don't explain the parallelogram way. At least, my past videos or my colleagues' videos that I linked. I'll teach it here though, because they're both helpful. Both of these methods are helpful. So that's 2 ways of finding the resultant. So really, we haven't done too much yet. We just defined vectors and explained how to add them together. But what about if we want to do more? So, for example, we could multiply a number to a vector. So you can multiply 3 to a vector. Guess what that's going to do?
Make it 3 times longer.
Make it 3 times longer. That's it. So, I need to turn this on. All right, cool. So, yeah, multiplying by a number like 3, which is make it 3 times larger, multiplied by 1/2, it makes it half the size. So, and normally, so naturally, it will increase the length by whatever you multiply by, and it will not change the direction. Unless you multiply by a negative number. Now, if you multiply by a negative number, well, of course, the length will still increase or decrease based off of whatever you're multiplying by. But with the negative imposed, basically where your arrowhead faces, so instead of a vector like this, the negative vector, the arrowhead just switches sides. That's it. You just move the arrowhead to the other side of the vector. And that would be a negative vector. And there's some examples down here we'll look at to sort of emphasize this, but just to give you an idea, that's what a negative vector does. It just will place the arrowhead of the vector on the other side. The zero vector is obtained from adding a number, or basically subtracting a vector from itself. So if you have a vector and you add its negative vector, then all you do is get what they call a zero, the zero vector. What does the zero vector look like? It's just a point. I'm going to draw this out again. There's an example where we look at this, but the zero vector has no direction and no magnitude. It's not a very exciting vector, but it is a vector. And vector subtraction pretty much goes off of the previous ideas. If you subtract a vector from another vector, you're pretty much adding the negative. And again, there's an example where we do something just like this. You would apply the negative to the ladder vector and then add appropriately. Which again, we'll see that coming up. There's a few down here that we'll look at. Let's go ahead and do that. So pretty much all those ideas I talked about above. I forgot to change this. This should be U, V, and W. Yeah, that was my fault. Forgot to change those. It should be U, V, and W. Makes sense because everything at the bottom is U's, V's, and W's. But in any case, problem 1, it wants 3U. So whatever U is, we're just going to make it 3 times larger. So it's going to be a much larger vector pointing in the same direction. That's it. That's 3U. And for problem 2, it's negative 2V. So what we're going to do is, well, the length of the segment increases by 2, so it's twice as long.
It's negative, so the arrowhead to the other end.
Yeah, so the arrowhead just gets put on the other end. So notice in V up here, the arrowhead is on the top right, but since there's a negative 2, we put the arrowhead on the other side. So that would be negative 2V. Then afterwards, we have V minus 2W. So this is how vector subtraction works. We need to first figure out negative 2W. We need to figure out that one, what it looks like first. And so that's going to be, it's going to be fairly large. So W is up in the top right. The arrowhead's going to be pushed to the other side. So we're taking W up here, pretending like that's what we're drawing is twice as large, and then putting the arrowhead on the other side because it's negative 2W. So that's the first step. And now the second step, we can look at it as V plus negative 2W. Well, we already figured out negative 2W. So now it's just adding vectors together. So again, we can do this in one of 2 ways. We could draw it V, and then where V ends, in fact, let me do this in different colors. So here's V, and then where V ends, we can start W. So, or negative 2W rather. So it's going to be this really long diagonal vector here. So that would be negative 2W. The resultant would be where the first vector starts to where the second vector ends. Just like that. So that would be the process of handling a subtraction of vectors. You have to figure out how the subtraction, or how the negative scalar applies to your ladder vector, and then you can add the 2 together once you know what it looks like. And so one more. You take a vector V, and you're adding it to its negative self. So how does that even, so what you would do if you were naive about this, how you would add these together is where the first vector ends, that's where the second vector begins. Which looks kind of confusing. But what this does is this negative vector pretty much undoes everything that you did before. And so what you get is a singular point as a vector. So really what this is, if you add a vector, or if you subtract a vector from itself, you get the 0 vector, which is just a point. The 0 vector is just a point. That's it. Does anyone have any questions up to here? If not, we're going to look at some applications of vectors. You might see this in a standard physics class or perhaps even an engineering class. So, two forces, and they give us two forces of various pounds act at a point in the plane, and they give us the angle between the two forces. So there's some point that is being acted upon by some force of 37.8 pounds, and then another force, which is larger, so I'm going to draw that out a little bit longer, of 53.7 pounds. And they tell us that the angle between the two is just 68.5 degrees. And then it wants us to find the magnitude of the resultant force. So it's using some buzzwords here. It wants us to find the length of the sum. That's dissecting all of the terminology. The length of the sum of the two vectors. So now we ask ourselves, well, how do we add two vectors together? Well, remember, there's two ways we can add vectors together. This goes back to your question. In this problem, it's already set up for us to use the parallelogram way, because illustrating it in that way requires both vectors to start from the same point. So we already have that by the mere setup of the problem. So to set up the parallelogram, so we need to construct a parallelogram from all the vectors, and we get exactly this here. I think I'm going to draw this out larger to really emphasize what's going on here. Okay, so some blues. Okay, so I'm just going to get rid of this. Okay, so now that we have the parallelogram set up, the resultant, the sum, is the vector that is really the diagonal. I'll use blue. That is the resultant. And we don't know it. We do not know what the length of the resultant is. So if anything, we can illustrate the resultant, but we don't know what the length is. So what we need to do is, well, this is when laws of sines and cosines comes into play. Because we have some triangles lying around. We actually have two triangles. Let's go ahead and bring all of this information. Let's go ahead and bring this together a little bit better. Since we have a parallelogram, a helpful thing is that there's some geometric properties that follow. So if anything, we can complete one of these triangles, at least in terms of saying, well, if the segment across, if this over here is 53.7, then the segment across is going to be 53.7 as parallelogram. So if anything, that triangle, that top triangle, it's sort of scalene in a sense. (37.8) and 53.7. So if anything, we have that. The problem is, well, we're looking for x down here, but we don't really know anything else. And you might think, well, we have the angle over here. But that angle is not this angle. Because when we drew the resultant, it split right through that whole 68.5 degrees. And you might think, all right, then it's just half of that. No, it's not, whatever that is, 34.25. It's not that. It is not a bisection. It just cuts an angle into two pieces. And we don't know what the sizes of them are. However, we go back to the idea of parallelograms. These angles have to be the same. The diagonal angles, which means something very particular about these angles that I'm highlighting in purple. What does that mean about them? Does anyone have any clue?
Well, they're going to be the same.
So you're saying these are the same? I mean, if so, that's true. Can you figure out what they are? What's the sum of an angles in a parallelogram?
When you subtract the 180
360.
minus,
I think you all have the right idea. So I'm just gonna say that the angle that I shaded in purple is the supplement of the 68.5. It's the supplement. All the angles have to add together to give you 360.
So those two would be 180. Any two.
So in essence, we actually are finding this angle. We're actually going to find this top angle because if anything, so what it comes down to, so this is a property. This is just a property in general. Adjacent angles in a parallelogram are supplements or supplementary. That's just a geometric property. So adjacent means next to. So angles next to each other are supplements, as in they add to 180. So really that angle is 180 degrees minus 68.5. Is that? That's 111.5 degrees? Yeah. So really that's what we found. So that's a little tricky, but Adjacent angles and parallelograms are supplementary. By using this, now we have a triangle with a sufficient amount of information to apply either the law of sines or the law of cosines. Does anyone happen to know which one we use,
Law of cosine.
and why is that?
We don't
Oops.
have two corresponding. That known.
Yeah, we do not have a corresponding side and angle pair. We do not have it at all. We don't know it. So in order to use the law of sines, we need one corresponding side and angle. But for the one angle we have, its corresponding side is x. The 37.8, its corresponding angle, I don't know. I don't know what that is. And the 53.7, same thing. We have to use the law of cosines then. So the law of cosines it says that in order to find x, we need to square 37.8 squared plus 53.7 squared minus 2 times 37.8 times 53.7 times the cosine of the angle. There we go. So really the majority of this is going to be plug it in your calculator. $37.8 squared plus 53.7 squared minus 2, 37.8, 53.7, cosine of 111.5. And if anything, I have that x squared is 5,800. We'll call it about 4.2. Doesn't really matter. So using some quick algebra, we just have to take the square roots. I'm just going to recycle the answer from before. So you should get something fairly similar. I just used the exact answer from before. If you use the approximated one, then you might be off by like 1,000th or 100th or something. It doesn't matter. But this would be the magnitude of the resultant force. This is it. Or in other words, if there are two forces acting upon a particular point, then the force in the resultant direction would be precisely 76.16 pounds. And I bet that's probably relevant in some application problem, but I can't think of anything offhand. The next problem is pretty similar. So if you are still a little bit fishy about this one, there's another one. Does anyone have any initial questions so far? If not, the next one is fairly similar. Because notice it's still two forces acting at a point, but now it wants us to find the angle. So now it's saying, well, we're going to tell you the resultant force length, and you're going to find the angle. So it's almost the same. So if anything, I'm going to go ahead and draw a nice grandiose diagram here. So still at a point, 128 pounds, and then this one much larger for no particular reason, 253 pounds. And really, they're just straight up, they're saying to find this angle right here, that entire angle. But the problem is if we find the resultant, the resultant splits that angle up into two parts, and it doesn't have to be a bisection. So it's not like the angle is just split in half. It's split in some way that we don't know about. And it says that this is 320 pounds. So now we need to find that angle in red. And it looks kind of messy because, well, the angle in red is seemingly just split in some, it's partitioned in some way. So the question is, well, how do we figure that out? And if anything, I want to complete a triangle somewhere. I'd like to complete one of these triangles. And I'm going to put the 253 up here, just like we did before. So now that top triangle is completed. And now we can go ahead and write that off to the side, because I think that'll be pretty helpful. So 128 here, 253 there, 320 here. Well, the problem is, if we're trying to find the red angle over here, well, this is not going to cut it. So really what we want to do is utilize the fact that if we find the top angle here, so if we find this top angle instead, which I'll just call, I don't know, capital A, doesn't really matter, then we know that the red angle, the one that we're trying to find, is a supplement to that, or supplementary to it. So really we're just working this problem the same way, but we're just looking for something different. So instead of looking for the unknown side, using ideas of supplements, we're looking for an angle. So do we use law of sines or cosines?
We're going to use cosines again. We don't have any angles.
That's right. We don't have any angles, so law of sines. And what do we take the sine of? Nothing. There's nothing to take the sine of. Law of cosines would be used here. So, and again, there's no completed pair. There's no angle segment angle segment pair that we can compare. So, law of cosines again. But this one's going to be the kind of unfortunate application. If anything, you have to make sure the numbers go in the right place. The segment across from the unknown angle has to be the one on the equals, the one isolated. So that's why I'm putting 320 here, and then the other two don't matter. Oops, forgot a 2. In fact, I just see myself running out of room. I'm just going to start this over. But if you know what I'm going to write, then just go ahead and write it. So 320 has to go first. And then that's equal to 128 squared plus 253 squared minus 2 times 128 times 253 times the cosine of A. And remember, this was the situation I mentioned last time in class, where you can't just put all the numbers together as you want to. Instead, you have to do it
128 squared plus 3 squared.
Yeah, so really the numbers you could put together, I mean, it depends on how good you are with algebra. So this would be 102400 is equal to 128 squared plus 253 squared. You can do that. Minus whatever that product is. And then you could subtract the 8393 on both sides to get 22007 is equal to negative 64768 cosine of A. So notice I'm not combining the number next to the cosine with the 80,000 number. They do not go together. That breaks order of operations. I know someone's going to do it on the midterm, and that'll be a pretty decent penalty. So I'm hoping this warning will keep you from doing that on the midterm. But we can go ahead and divide both sides now. 22007 divided by negative 64768. And then finally, we take inverse cosine of both sides. So inverse cosine of 22007 divided by negative 64768, close parentheses. Finally, we get 109.86 degrees. And we're done. Why are we not done?
We haven't found the other, like the total angle.
Yeah, we found the supplement of the right answer.
We have to subtract 180 minus 109.86.
Yep. Yep. That's one more step. It's pretty much just another, punch in the gut.
Something easy though, at least.
What's that?
At least it's something easy.
Well, as long as the rest of you find it easy, I guess in comparison to this, just the law of cosines is just a very wonky formula. It's pretty much the quadratic formula of trig. But in any case, we found that, so what we found was this angle up here, but we didn't find the original angle, but we're just one step away. We need to find the supplement. So in red, I'll do it up here. So the angle, I'll just call it capital X. It's 180 degrees minus the 109.86 degrees. Whatever that is.
71.4.
Yeah, we'll just round it to decimal places. That's fine. Degrees, and that would be your final answer. I know, very fun. You put this into some program and it would just spit it out in like a second. You didn't have to do all the derivation steps. I guess you can write out a quick formula for this. A would be the inverse cosine of, how does that work? Little a squared divided by b squared plus c squared, or I already screwed it up. You can write a formula out of this. It's not too bad. Minus b squared minus c squared divided by negative 2bc. Yeah, nothing too bad. You can make a form. So you can implement this in some solver and it would do everything for you. The reason it took so long for us was because we didn't have this formula written out for us. We had to derive it. Of course, the computer says, well, screw that, just, give me the formula. I'll take care of it. But in any case, does anyone have any questions before we look at more vector application problems? So we will move on to Example 6. So there's a car parked on a hill. So I'll draw my hill very basically. And the car will be even more basic. I cannot draw at all. So that's car. Car has weight. Which direction does weight go in? Straight down. So if this is 3,000 pound car, this is 3,000. It wants us to find the force required to keep this massive car on the hill, if anything. So the force required, I'm going to write that in red. The force required to keep the car on the hill. So imagine you're trying to tug this car up a hill and there's some rope attached to it.
Is that drive or neutral?
Oh man, come on. We're not going to start talking about friction here.
I don't want to.
If that, I'll go bring up, I'll go email Dr. Norwood or something in the physics department. He'll give you a nice lecture on that.
Probably a whole class for this one problem.
Oh yeah, no doubt. Yeah, that would be a true physics problem.
Yeah.
So that's what we're looking for, and they also give us an angle. They tell us the angle of incline. So they actually tell us this angle. It's 15 degrees. So really, now that I'm looking at it, and I always do this, I was going to explain it one way that seemed kind of fishy to me, but I'm looking at it now and I think I see an even better way to explain it. Let's give it a shot. So what I wanted to do, well, regardless of the way I was going to explain it, I don't see a triangle anywhere. And the reason why I don't recommend the parallelogram method here is because a part of this problem requires you to derive a right triangle. And I just don't see, I've been yet to see why this problem you get to have a right triangle doing it the parallelogram way as opposed to the previous problem. But if you derive the resultant in a different way, then just this is what I mean. So this is the way I'm going to explain it. I'm going to take all this information by drawing that starting point. I'm just going to draw it again. If anything, the x is going upwards. But we know, so I'm going to use transversals, and all that means in this case is if I drew another straight line right here, the angle is going to be the same right here. That's all I'm using from transversals.
They correspond.
They correspond. So basically I'm just moving the ground up. That's all I'm doing here. I'm moving the ground up. And the only reason I'm doing that is so I can force a triangle. I'm pretty much trying to move all the quantities together. So if anything, now that ground has been moved up. So what that represents, so you can slowly see that I'm building it all from right here. So really that 15 degrees gets moved right here. And then,
We could move 3,000.
yeah, so the 3,000, so this is where the resultant comes into play.
You'll put it at the end.
Yeah, you would put it at the end. So this would be the resultant. And so that, in this incarnation, would form a right triangle. See, I always do that. I always think of a better solution as I'm teaching. I think that's a lot more intuitive than the other way I was thinking. So that's what I got. So now we have a triangle, in other words, and we have a right triangle. And doing it this way, it's a lot more obvious that it is a right triangle, as opposed to if you were to draw a parallelogram.
Yeah, that's ugly.
It didn't seem too natural to me. The book, I was reading the book, and the book said, and you get a right triangle. I didn't like that.
Where, is it on the 3,000? Is that where they're, like where it meets at? Is that the right?
Yeah, that's the right triangle would be, well, you would have the resultant right here, and then that would be the right triangle, which I didn't like how this problem, if we use the parallelogram method, this one you get a right triangle, but the previous problem you don't. And I couldn't think of a good way in my mind to think about how to convey that. So I think this is a more intuitive approach. I mean, the problem really works out. I mean, pretty much everyone got this problem right last semester. So it works out really nicely because notice, you have a right triangle. Guess what you get to use when you have right triangles?
Sine.
Yeah, sine. Yeah, you don't have to use stupid law of cosines because you have a right triangle, not just a regular triangle. You get a right triangle. Use law of cosines and sines. That extra difficulty lies whenever you do not have a right triangle. So,
It'll become an algebra problem, basically.
what's that?
It's going to become an algebra problem, basically.
Yeah, it's going to be a fairly quick algebra problem. So, if anything, the reason why sine should come up quickly is because what's opposite of sine? That's the 3,000. And then the hypotenuse is x. So I guess I'll put in the intermediate step as well. Multiply both sides by x. You're basically swapping x and sine of 15. And so what we're finding here, it's the force required. So we're not finding an angle, because that'd be a pretty large angle. We are finding a force. So that would be the final answer. And the next problem is pretty similar. I guess before I move on to the next problem, does anyone have any questions about this problem? So if not, example 7 shall be where I resume. So,
Whenever I put that in the calculator, that's not the answer I got.
oh, it's not? What did I do wrong then? Oh, I forgot the divide sign. I just put times. Okay, sorry about that. Oh, yeah, that's a much larger quantity. Wow. Okay, sorry about that. I forgot how calculators work. 11591.11. Cool, good. All right, my fault. So that's a lot more force required. Okay, so let's move on to example 7. So it's pretty much the same situation, just a boat instead of a car. I'm going to draw it the same way. So, boat. It has a force of 500 pounds being pulled. So if anything, they're giving us this value now. So now they're giving us this value. They still tell us the angle, which is 18. And we want to figure out how much does the boat weigh. So it's flipping 2 of the values. Instead of knowing the weight and finding the force, we're given the force and we're finding the weight. So that's all it did, it just switched. So as you would imagine, this problem is going to be very similar. So again, I'd like to look at it as moving the ground up in essence, which means the 18 degrees in this problem will go right here. We'll go ahead and redraw this. So now we have the 500. We have the 18 degrees. And then the resultant would come straight down to give us x here. So,
Is that a right triangle or?
yeah,
I was just asking.
yeah, it's a right triangle. So, really, we even use the same trig function. Everything's still in the same spot. So, sine, so it's still opposite over hypotenuse. This one's even easier because it's less algebra. So how much does this
Don't have to worry about any division symbols in that one.
Yeah, my saving grace. No division in this one. So I can't screw it up now, I hope. So the boat weighs 154.51 pounds. I'm double checking this one. Okay, cool. All right, cool. Does anyone have any questions about this? When should I make this homework due? Because there's homework for this section, and I have to pick it up sometime. Let's see.
What section is this for?
Oh, that's a good question. It's going to be 7.4 in the book. And the next one's 7.5, in case I forget to say it. This is 7.4 in the book. So, yeah, I should probably give this a due date. See, today is Tuesday. You're turning in stuff on Thursday. So next Tuesday, I don't think I'll get done with the next section. So For now, this homework is due next Tuesday. It's due a week from today. Some miracle I get done with the next section, I'll make those two concurrently do the following Thursday, which I doubt I will. If anything, this homework is going to be due next week. It's going to be a lot of diagrams, so you might be able to knock it out fairly quick. Okay. So this section that we just finished, that homework's due a week from today. The law of sines and cosine homework, so that's 2 sections, not 1, that's 2 sections. It's due Thursday. You can ask me questions after class about it today. Let's go ahead and move on to algebraically defined vectors and the dot product. Before I forget, this is 7.5 in the book. 7.5. So really, we're going to quantify this more so to a coordinate plane, which means we'll start to incorporate a little bit more of the trigonometric ideas as well. We do have a position vector. We were talking about vectors. What is a position vector? And so it's pretty much a vector that is now, well, I guess we're specifying the vector relative to a coordinate plane. So we're moving just a vector in space with no sort of coordinate system. Now we're putting it on a coordinate system. And with this refined approach, we can do some interesting stuff with it. So there's a notation that we use. A vector has coordinates. A vector can be treated like an ordered pair. Almost. It's not an ordered pair, but it's treated like an ordered pair. So as I explain this, I'll start talking about example 1 here. So notice they use these, I'm trying to avoid calling them, their mathematical syntax term is called, we call it a lingle-ringle. It's left angle, right angle. But the code to type that into the computers, it's an inside joke. Never mind. It's just a bad inside joke. But it's we use this angle notation instead of parentheses to distinguish it from just a standard ordered pair. And if you want to, so this represents a vector. And if you want to plot this vector, then what you would do is you would plot it as if it's an ordered pair. So it'd be 1, 2, 3, 4, 5, 6, 7. You go up 24 times, a whole bunch of times you go up. So you would plot it as if it were an ordered pair, but then you draw a vector connecting to that point from the origin. So that would be the vector -7, 24. So this is part of the utility of moving a vector to a coordinate system, is if anything, now we can give it specific identity. Now we give it an X and a Y coordinate in essence, or component rather, as they go on to define it. X component, Y component. So in addition to this,
We can triangulate. Now we can triangulate if we needed to find like signs and stuff. Or are we gonna be doing any of that?
well,
Not to find out.
yeah, about to find out. The magnitude is still a thing, but now that we have coordinates, we could figure out the magnitude. Hey, that looks kind of familiar. I feel like we've seen this before. Yeah, that's the Pythagorean theorem. In fact, they went ahead and threw in the square root for us as well. How nice. So we have that as well. So, in fact, I'm just going to move that notation off to the other side. So what did I have here? I had -7, 24. So if I wanted to find the magnitude of this vector here, which I'll call it X, well, if we Well, if only there was a way to sort of form a right triangle out of this. Oh, wait a minute. That's exactly why this is super helpful, because we can triangulate. Which is why the Pythagorean theorem comes into play. So really, if we call this vector, I guess to match the notation, if we call this vector u, then the magnitude, so I'll just write it out. The magnitude of u, it's u with the bars. That's what the magnitude is in notation speak. It's the square root of the components squared. So -7 quantity squared plus 24 quantity squared. And I'm pretty sure this is a special triangle. I think this is 25. Let me check. 7 squared plus 24 squared is 625. And yeah, that's a perfect square. That's 25. Cool. So if anything, the magnitude works out very similarly. So if you want to determine the magnitude of a vector, given the components, you can use Pythagorean's theorem. And there's also the positive angle between the x-axis and the position vector is called the direction vector, or a direction angle rather. So really, the direction angle, well, it's this angle. Again, this is where the vectors being moved to a coordinate plane helps us be able to recycle a lot of information we've talked about before. So in this problem, how do we figure out that angle?
First, you have to find the reference angle, right? By using the triangle.
Yeah, how do we find a reference angle?
180 minus that angle,
Minus what?
the angle that we don't know.
Exactly. So how do we find that angle we don't know?
Wouldn't we have to use that triangle to find the smaller reference angle?
So how do we use that triangle to find the smaller reference angle?
So x would be 25. That's the hypotenuse. So then you
So let's do it this way.
and then say you could use sine.
So we have a triangle. So the reference angle is a good idea to go off of. So we can find the reference angle.
So -7 is the bottom one,
And -7 is the bottom one because we went to the left 7.
and then 24 is this one on the side.
24 is that one.
So you could use sine of that angle.
So I'm going to put the theta with the prime because that's the reference angle. And yeah, we could use
Sine.
sine. We can use any of them really.
Can't do any of
I mean, the reason why it's good to use sine is because we want a positive angle. And sine is positive in the second quadrant. So what's sine here? That would be 24 over 25. So to figure out the reference angle, we need to take sine inverse. What is that, like 73.7-ish?
it. 73.7. 74.
I just have it written right here. I'm cheating.
Dude, I was going to say, no way.
Yeah, I'm cheating big time. I don't have my McLaurin series memorized, so I can't do it in my head. 73.7 degrees. So that's the reference angle. If you were to use tangent instead, you would get negative of this, and then you just get rid of the negative. In any case,
So now it's to find that angle, it's 180 minus 73.7.
yep. 180 minus 73.7. 100, 106.3 degrees. Cool. So that would be the direction angle. This is the direction angle. So the reference angle definitely helps. So cool so far. Cool. All right. Let's see. I think I'm gonna do probably example 2, and I'm kind of tired. I think example 2 would be good enough. So example 2. So they give us these formulas. Which is, if you're given the magnitude and you're given the angle between two, really between two vectors, I guess one of the vectors is fixed. So in other words, if you're given the magnitude and the direction angle, then you could figure out the components of the vector. So in the problem above, we took the x and the y component, and we found the magnitude and the direction angle.
You can use the magnitude and the direction angle.
Yeah,
Basically
we can go backwards. We can go backwards with it as well. And normally this one's pretty easy. It's just formulaic. But it's to figure out the x component. I don't know why they call it a. It says take the magnitude and then multiply that by cosine of 20 degrees. And then find the y component, which they call it b for whatever reason. You would just do this and this. So this one's a pretty quick computation. And this is telling you the components of the vector itself. So after you apply these quick computations, the vector, as it would be notated, so if you get this as a homework problem and you just do these computations, I mean, that's all nice and everything, but follow through with a conclusion. Follow through with a conclusion. Just because you did the sufficient amount of computations, I mean, it's always just good practice to have a reasonable conclusion. That's just in general. But besides for that, I think I'm going to call it a day there. It's a good amount of information. So again, midterm is going to be 2 weeks from today. You have to let me know by Thursday if you're taking the exam remotely. If not, it's going to be assumed that you're taking it in class. Which means you have to show up here and take it in person. You just have to see who you are. So other than that, that's all I got. If you have any questions, I'll stick around. Have a good day.